Okay, welcome to the fourth and final video of Lecture 17 regarding combined heat and power. So we learned about heat engines, we learned about the Rankine cycle, we learned about heat pumps. Now we're going to combine all of that into one idea, combined heat and power. So the efficiency of a standard power plant, say a Rankine cycle running power plant burning coal, is going to be anywhere in the range of 30 to 40%. Pretty dismal. Likewise, the efficiency of a heater, a combustion heater, something burning gas to generate heat, is going to be 40 to 50%. Which you say, wait, that's not what I've heard. Well, this is after we consider the inefficiencies of the actual combustion process. Because combustion is what we call irreversible. You can't make combustion go in the opposite direction, right? It's very irreversible. And this means that a lot of that energy is kind of used to generate that irreversibility. So when we burn gasoline, we're actually not able ever to use as much of that energy as we would like. So some idea then is, well, what if instead of doing these two things separate, we realize that a power plant, remember this was the efficiency of a power plant, generates waste heat, and that waste heat already has, generated that irreversibility. So if we combine these ideas and use the waste heat from a power plant for something useful instead of just rejecting it into a river or something, then we can get efficiencies up to 65 to 80% for a CHP, or combined heat and power. Meaning that instead of just wasting the exhaust gas from a large power plant, we use those exhaust gases for actual heat. This is not a new idea. This is the very first central power station built by Thomas Edison in the middle of New York City. Imagine a power plant in the middle of New York City. Well, here it is. And guess what they did with all the waste heat? The waste heat from this power plant was used for heating. I imagine that was one way they convinced people to let them build a power plant. And what happened? Well, as power plants got bigger, we had to put them further away, and now power plants are far away. So they are far from heating need. So where we need heat is in buildings, and where the power plants are is far away from all the buildings. So what CHP technology really focuses on is putting small power plants, sorry, my pen is wigging out. So we have small power plants, and they are located where heat is needed. So the point of CHP is small plants located in just the right spot. So obviously we're not going to throw a nuclear power plant in the middle of Dayton, right? So we're going to kind of utilize a different set of technologies here. Things like microturbines, essentially a tiny Rankine cycle built into a box, which you put in the basement of a building. That Rankine cycle generates power for the building, and the waste heat is used to heat the building. Likewise, we have what we'll call small turbines. These are larger boxes, in fact, a real plant, but a very small power plant, something you might install on a college campus and generate enough power for the campus and enough hot air then for the campus as well. Also, think of a very large reciprocating engine. We're talking a huge diesel engine, maybe that might go on a boat. And this you could put to generate power for a small neighborhood, and the exhaust gases could heat that neighborhood. Also, fuel cells, which convert fuel directly into electricity without combustion, erasing that irreversibility, generate waste heat. And these fuel cells are nice because they are silent and generally small. finally, one more actually very useful technology. Oh, I spelled that wrong. Absorption refrigeration. We're not going to go over how this works exactly, but instead of a pump, remember we reviewed the vapor compression cycle in the last video, and there was a turbine that we used to compress the vapor. Well, instead of having a turbine, we actually use heat to compress the vapor. That's pretty cool, right? So with waste heat, we can get compression, and we can actually get then cooling. So you can run an air conditioning system using waste heat. Okay, and based on a report from ACEEE, there's currently 240 gigawatts of potential CHP out there in the United States, and that's just looking at industrial applications. So they're looking at large campuses, large factories, etc. How much could we install small power plants at all of these and use that excess waste heat to heat those places? Okay, there's another idea associated with combined heat and power, actually a much more popular idea, the combined cycle power plant. So a combined cycle power plant is when exhaust gases from one power plant, a high temperature power plant, feed into a separate power plant. So it's best to kind of draw an example here. So we have a high temperature reservoir and we have a cold temperature reservoir. Before we've drawn one heat engine operating between these two reservoirs. Well, we're going to ditch that idea. We're going to say, well, what about two heat engines? Okay, so we're going to transfer heat from our very high temperature source. In this case, this would be the temperature of combusting natural gas, because natural gas is generally a small hydrocarbon and actually has a very high temperature of combustion. And we can use that in a heat engine that runs a different cycle called the Brayton cycle. You've used the Brayton cycle all the time because any jet engine uses the Brayton cycle. So using air as a working fluid in combusting natural gas, we can get some work out from this Brayton cycle. Imagine a huge jet engine strapped to the floor. They're turning a big shaft and extracting energy. So we get some work out from this Brayton cycle. But then, right here, this waste heat then feeds right into the boiler of a Rankine cycle. So instead of burning coal to generate heat in a boiler, we just use only exhaust gases, the waste heat from our Brayton cycle, to power our Rankine cycle. And then we now have true exhaust gases leaving the Rankine cycle, and these even could be used for process heating. That's called a I think it's a tricycle plant or something like that. Anyway, so you see, by stacking these two power plants together, we actually get much better efficiencies. So the efficiency of a standard combined cycle plant can be something like 65% for a power plant. That's not even using the waste gases. That's amazing. That beats coal, or a single Brayton cycle blows it out of the water. Which is why combined cycle is undoubtedly the most popular form of power generation technology in terms of new construction. So here you see from 2002 to 2018, the growth of a combined cycle compared to the decay of coal. And this is because combined cycle makes so much economic sense, right? Much better efficiency means less fuel for the same amount of electricity. Also, natural gas is cheap because of fracking. So fracking is one, the combined cycle natural gas plant is one result of the popularity of fracking, actually. Okay, so that's combined heat and power and combined cycle plants in the United States. that is it for our power plant review. We're going to now go on to geothermal.